This was the very first problem in the history of the International Mathematical Olympiad. It was given in 1959, and at first glance it looks almost too simple. For every positive integer n, prove that the fraction 21n plus 4 divided by 14n plus 3 is already in lowest terms. In other words, no matter what value of n we choose, the numerator and denominator can never share a common factor greater than 1. But how can one argument control infinitely many fractions at once? The answer is that these two expressions secretly contain the number 1. And once we find it, the entire problem collapses. Let d be a common divisor of the numerator and denominator. Then d divides 21n plus 4, and d divides 14n plus 3. A common divisor must also divide the difference of the two numbers. Subtracting gives the quantity 21n plus 4 minus the quantity 14n plus 3 equals 7n plus 1. Therefore, d divides 7n plus 1. Now, combine the two facts. D divides 14n plus 3, and d divides 7n plus 1. The number d must divide every integer combination of these two expressions. In particular, it divides the quantity 14n plus 3 minus 2 times the quantity 7n plus 1. But this expression is exactly 1. Therefore, d divides 1. The only positive divisor of 1 is 1 itself, so d equals 1. Hence, the greatest common divisor of 21n plus 4 and 14n plus 3 is 1. And the fraction is irreducible for every positive integer n. That is the Euclidean algorithm hiding inside the problem. First, the coefficient of n drops from 21 to 7. Then, n disappears completely. The entire first proof can be compressed into one identity. 3 times the quantity 14n plus 3 minus 2 times the quantity 21n plus 4 equals 1. Any common divisor of 21n plus 4 and 14n plus 3 must divide the left-hand side, so it must divide 1. That one identity proves the result for every n. Now let us read the same identity in the language of modular arithmetic. Suppose the numerator and denominator share a prime divisor p. Then 21n plus 4 is congruent to 0 modulo p, and 14n plus 3 is congruent to 0 modulo p. Multiply the first congruence by 2. We get 42n plus 8 is congruent to 0 modulo p. Multiply the second congruence by 3. We get 42n plus 9 is congruent to 0 modulo p. Now the n terms are identical, but the constant terms are consecutive integers. Subtracting the two congruences gives 1 is congruent to 0 modulo p. That is impossible for any prime p. So no prime can divide both the numerator and the denominator. Again, the fraction must already be in lowest terms. The first proof reduces the expressions until 1 appears. The second proof aligns the expressions until 1 appears. They are two views of the same hidden identity. Now compare the given fraction with the much simpler fraction 3/2. Their cross-product difference is 3 times the quantity 14n plus 3 minus 2 times the quantity 21n plus 4. And we already know that this equals 1. This determinant 1 pattern is the signature behind fairy neighbors. But before using that name, notice what the identity forces. Suppose 21n plus 4 and 14n plus 3 had a common divisor d greater than 1. Then 3 times the quantity 14n plus 3 would be divisible by d, and 2 times the quantity 21n plus 4 would also be divisible by d. Their difference would therefore be divisible by d, but their difference is 1. That is impossible. So the original fraction is reduced. Now the geometric interpretation becomes valid. Because the two reduced fractions have cross-product difference 1, the given fraction and 3/2 are neighbors in an appropriate Ferry sequence. The Ferry viewpoint does not change the arithmetic. It reveals the structure hidden inside it. The original fraction is locked next to 3/2 by a determinant of 1. 3 viewpoints. 3 different mathematical languages. The Euclidean algorithm reduces. Modular arithmetic aligns. And Ferry fractions interpret. But all 3 are driven by the same identity. 3 times the quantity 14n plus 3 minus 2 times the quantity 21n plus 4 equals 1. The first problem in International Mathematical Olympiad history was not about complicated computation. It was about choosing the right combination. And hidden inside two expressions depending on n, there was always a 1.